Okay, so welcome back. Now in the last video we talked about the conscious snowflake, and I just wanted to remind you that it may seem like certain things are impossible, like how do we have a snowflake that has an infinite perimeter but has a finite area? Now I just want to remind you that we've had other examples of things like this happening. For example, remember Gabriel's horn, right? So we had this curve of 1 over x squared, right, that has a curve starting from 1 to infinity, right? So we had the improper integral of 1 over x squared, and when we calculated the area, it had a finite area, right? Surface area. But it had an infinite perimeter, if you will. Okay, so we've seen other situations like this where one value is infinite and another value that's related is finite. So again, these things, even though they seem impossible to have, they seem like they contradict, they don't. Okay, so we've seen other things like that occur. But anyway, just wanted to leave you with that. Now, today what we're going to do is we're going to turn our attention to a really interesting topic called telescoping series. This is a lot of fun. If you realize that you have a telescoping series, things can become very simple very quick. And what do we mean by a telescoping series? Think about in the olden days, back in maritime, let's say a few hundred years ago in the 1400s or earlier, you had telescopes, right? Well, the telescopes, like the ones that the captain of the ship would use, would be what we call telescoping lens, right? A telescoping lens where it would collapse, right? He'd keep it in his pocket or around his belt or whatever, and he would take it out and he would and look through it. And then when he was done, it would collapse. Well, telescoping series kind of behaves the same way. At some point, you'll notice that, hey, this thing will collapse and become really simple. So let's look at an example. So here's one that we looked at before. This is a series, and this is the one that had a really interesting result. Okay, so remember this is the series, and we represented the partial sum. We found that the partial sum is equal to k over k plus 1. Okay, and so if we write out the several of the partial sums, like we did before, what do we get? Okay. We get, I'll do it over here. So we get S1 is equal to 1/2, right? Right, so S1 is equal to 1/2, and then S2 was equal to 2/3, and S3 was equal to 3/4, and so on, right? So now, let's define this differently. So if I use partial fractions on this, right, I can rewrite this like this. So I can rewrite the series in an equivalent manner. N equals 1 to infinity, and this, by using the technique of partial fractions, this becomes 1 over what? This is going to become 1 over n minus 1 over n plus 1. Okay, so again, verify that on your own, okay? Go through the technique, you'll find that it is going to be 1 over n minus the quantity 1 over n plus 1. Okay, so now we can write the series like this. Okay, so for n equals 1 to infinity, what do we get? Well, this is going to be what? It's going to be, let me write out the first several of these. So it's going to be 1, so it'll be 1 minus 1/2 plus, and then the next one is going to be what? For 2, it's going to be 1/2 minus 1/3. And the next one is going to be 1/3 minus 1/4. Right? Just like that. Now, do you notice something happening here? Well, notice that we have a minus 1/2. Well, let me write it out one more step. Okay, let me write it out one more step. So now this is going to, I'm going to drop the parentheses, right? And I'm going to move things around. So this is going to equal 1, and then I've got minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. Oops. And so, what's happening here? Well, notice that the middle terms here are canceling each other out all the way till you get to what? Well, it goes on for infinity, but except for the last term. The last term, because if you stop somewhere, any partial sum, right? Any partial sum is going to stop somewhere, and so it's going to be the first term and the last term. All the middle terms cancel out. We've seen that before, right? That's what happened before. Now we can see it more clearly because of the way we're writing this, okay? But the same thing happened when we were looking at this before, okay? So now, let's look at the partial sums using this, okay? So, if again, I'm going to erase this. Let's use this new form. So again, I'm going to write this as the series of 1 over n minus 1 over n plus 1. Okay? So now, let's look at the partial sums. Okay? So S1 is going to equal 1 minus 1/2. S2 is going to end up equaling 1 minus what? Well, the middle terms are going to be canceling out, so I'm going to end up with 1 minus 1/3. And then S sub 3 is I'm going to end up with 1 minus 1/4. Right? And so on. So what's going to happen? I'm just going to end up with what? In the end, my S sub k, right? So notice what's happening here. So my S sub k is just going to equal 1 minus what? 1 over k plus 1. Okay? So where is this taking us? So if we look at the sequence of partial sums, right? So we notice that the middle terms cancel each other out, leaving only the first and last terms, like I said earlier. In a sense, the series collapses, again, like one of those telescoping lenses, or what they call a spyglass. Okay? And so you can, again, change the length of the telescope, just like this collapses into a much shorter calculation. Okay, now, so now, what happens? Well, as k goes to infinity, right? As k goes to infinity, this is going to 0. So what does that mean? It means that the sequence of partial sums converges to 1, and therefore the series also converges to 1, which we found out before. Okay, so the sequence of partial sums converges to 1 as k approaches infinity. So therefore, what? Therefore, the series n equals 1 to infinity also converges to 1. And that's it. Is there anything else I want to say about this? Okay, so next we'll give the definition of a telescoping series. See you then.